Ladies and gentlemen, hello and welcome. Coming to you not quite live from One Take Studios, where today's topic is inverses. Inverses of relations, inverses of functions, inverses of everything. Just by way of remembering, relations are things that are paired together but don't necessarily follow the rules of a function. We said for a function, every x has to have one y and one y only. So you might want to keep that in your brain, just in the back part someplace. All right, here's some examples of what we would see for inverses. So I have two examples here for you. Here's the first one, 2 plus negative 2. Those two are inverses. So for some of you, your brain just said, oh, inverses are opposites. Sometimes that's true. This is 3 times 1/3. These are inverses of each other. Like, oh, that means that inverses are reciprocals. Sometimes that's true, but not always. All right, so here's the thing. Sometimes we have opposites, sometimes we have reciprocals, but here's the message that I need you to come away with. Inverses undo each other. So whatever operation, whatever form that takes, inverses will undo each other. A negative 2 will undo a positive 2. Multiplying 3 by its reciprocal 1/3 will undo each other. They don't even get you the same outcome, and that's fine. 2 plus negative 2 is 0. 3 times 1/3 is 1. So as long as they are undoing each other, that's what we describe as being inverses. All right, now, official news, ladies and gentlemen. Officially, this is our statement right here. Ta-dun, ta-dun, ta-dun. Functions are inverses if, oh, what the heck is that going on there? F of g of x equals x and g of f of x equals x. Because, right, yeah. What does that mean? Those are called compositions. And what this means is I'm going to take function g, I'm going to plug it into function f. And then I'm going to take function f, I'm going to plug it into function g, and I'm going to see if they will undo each other, which would leave me with x and only x, because all of the other numbers, everything else would be undone. All right, so whole bottom of this page is dedicated to trying to decide if f of x, which in this case happens to be defined as 3x minus 21, is truly an inverse with g of x, which is 1/3 x plus 7. Now, for all of you people out there who like to eyeball things, stop it. Cut it out, all right? Because they're like, ooh, 3 and 1/3, those are inverses. Clearly that works. And minus 21, well, the inverse of minus 21 should be plus 21. Stop. Stop and think and work. So here's what's going to happen. I'm going to do a little bit of color coding here. I'm going to call this f of x my blue equation right here. There we go. And for this one, this is going to be my purple one right here. And I'm trying to plug one into the other. So for starters, here's what that would look like. F of, and I'm going to try to make this as clear as I possibly can, f of g of x. So in other words, what I'm doing right now is I am taking this purple function and I'm plugging it into the other function, again, in place of x. What does that look like? Well, here's the x, here's the function. So this whole chunk right here, this whole chunk, is going to go in place of this x. Substitution, all right? Substitution. We're not multiplying these functions together. I know that's kind of what it looks like, but that's not it. So this says 3 times x minus 21. So we're going to do 3 times, well, x is being replaced with this function. So 3 times 1/3 x plus 7 minus 21. We have the 3, we have the minus 21, but we've taken the x out and put the 1/3 x plus 7 in its place, okay? See what happens with this. Watch this. So if we distribute the 3, because that's what should happen, 3 times 1/3, well, that's going to be 1x, and 3 times 7, that's going to be plus 21, and then minus 20. Hey, guys, look at that. X plus 21 minus 21 is x. We were kind of hoping that would happen. If f of g of x equals x, we're halfway there. All right, well, we need to test it the other way around. Both of these statements have to be true to technically call these two functions inverses of each other. So let's see if we can make it work the other way around. Here is g of x, and again, sorry, g of f of x, excuse me. F of x is going to go right here. Okay. This time, we are taking and we are plugging f of x into g of x. So in other words, this whole mess right here is going to go here, right here, right here, right here, in place of the x, just like we did last time, but reversed. So this whole function, f of x, is going into function g. That's what we've got. So 1/3 times x plus 7, that's going to be 1/3 times, well, it's not x anymore. We are substituting, we are replacing that with 3x minus 21. and then plus 7. So again, all the parts are there, the 1/3, the plus 7, the 1/3, the plus 7. The x came out, 3x minus 21 is in its place. Sorry, my handwriting is looking kind of sloppy today. Ugh, rawr, okay. Again, simplify, distribute. What's 1/3 times 3x? Well, that's going to equal x. And what is 1/3 of 21? Oh, minus 7 plus, hey, guys, x minus 7 plus 7 is x. These two operations completely undid each other. These two completely undid each other. Therefore, f of x and g of x are inverse functions. Everything else was dismantled, everything else was gone. So by our official definition, f of x and g of x, these two functions are inverses of each other. Great, awesome. Now, that doesn't quite get at what I want you to know right about now. Ladies and gentlemen, we have one overarching fact that I would like to make sure that you take with you today, pretty please, with sugar on top. The foundation of all things inverse is that x and y switch places. So while the official definition is nice, this is going to be a lot more meaningful to us. So pretty, make it pretty, party zone right there. Ladies and gentlemen, decorate it in your notes. There we go. The foundation of all things inverse is that x and y switch places. Why is my picture fuzzy? Make it stop being fuzzy. There we go. Okay. Life, rawr. Okay, so to show you what this might look like, I actually want to borrow a graph over here. And here's my graph, yay me. We've got just 4 ordered pairs right here. Got a graph, we're gonna put them in place. So 0, 1, 0, 1 is here on the y-axis. I am counting by 2s. 1, 4, 1, 4 would be here. 2, 9, 2, 9, and 3, 16, 3, 16 is here. So if we connect these right now, these 4 points, 2, it's kind of straight-ish. There we go, there we go. Actually, because I don't know where it's headed next, I'm not going to extend past that point at all. We have this slightly curved segment going on. What did I just say was the foundation of all things inverse? Boom, foundation of all things inverse, x and y switch places. So, ladies and gentlemen, if this is my original relation, remember relation is just a set of ordered pairs, this one does also happen to be a function, what would the inverse look like? If x and y switch places, please take that literally, x and y switch places. So this ordered pair was 0, 1, it's going to be 1, 0 for the inverse. This was 1, 4, this is 4, 1 for the inverse. X and y literally switch places, turn them around. So the inverse of this, well, let's graph it and take a look at that one, shall we? 1, 0, 1, 0 is now on the x-axis instead of the y-axis. 4, 1, that's over here. 9, 2 would be right here. And then 16, 3, 16, 3 is right here. So, right there, that is it. That is it. So, again, a little bit of color. This was our first graph, and this was our line right here. I'm going to edge it in blue. Okay. And this was our inverse right here. We switched the x's and the y's. I'm going to edge that in purple just so we can see it a little bit better, see the distinction between the two of them. All right, ladies and gentlemen, x and y switch places. Awesome. Do me a favor, go back to domain and range for blue. Okay, domain and range. The x's go as low as 0. The x's go as high as 3. So I'm not going to do my super formal writing right now. I'm going to say x is less than or equal to, 0 is less than or equal to x, which is less than or equal to 3. So all of the x's between 0 and 3. And my y's were from 1 to 16, and I connected that. So 1 is less than or equal to y, which is less than or equal to 16. When we say the x and y switch places, please remember that domain is x and range is y. So what does that mean? Or, excuse me, what does that mean over here? What does that mean for my domain and range? Again, they literally switch places with this. So if I look at this, my domain over here is what my range was over here. So I'm talking about all of the x's between 1 and 16. That looks sloppy, I'll fix it, there we go. There we go. And my range here is the same as the domain was over here because x and y switch places. So everything from 0 to 3. There we go. X and y switch places. Now, what is the one place on the graph where x's and y's could switch places and nobody would notice? What if we had the equation y equals x? Y equals x, right there. if y equals x and I switch places in x and y, will you be able to tell? I don't think so. So why is that important? Well, I'm going to take my trusty ruler here and I'm going to draw the graph for y equals x, which goes to the origin and has a slope of 1. If I can bother to manage that, yay me, there we go. All right, ladies and gentlemen, that is the line of y equals x. And if you look at that, check it out. That also happens to be a line of symmetry between these two graphs. That is always the case. So visually, if you're wondering, do I have inverses here? If the two graphs that you have y equals x as a line of symmetry, then yes, that's another visual way to tell what an inverse might look like. All right, so we have just said that y equals x is the line of symmetry for inverses, and that is always true. Okay, such a pretty line up there. Okay, so x's and y's switch places, which means domain and range switch places, which means we can see a visual on it. Okay, I like all this stuff. So let's go back to, for a moment please, this piece of paper right here, and pray that everything comes back into focus. Pretty please with sugar on top. Come on, you know you want to. Okay, there we go. So how do I apply that to the process then of finding an inverse? We looked at what it officially would look like to test inverses to see if they are inverses or not, but what if I just have one function and I would like to know what its inverse is? What is the foundation of all things inverse? X's and y's switch places. So if you look at this function, f of x is the same thing as y. So f of x equals 2/3 x plus 2. I'm going to call it y equals 2/3 x plus 2. And if the foundation of all things inverse is x and y switch places, I'm going to literally make them switch places. I'm going to put the x over here, equals everything else stays put. The 2/3 stays put. The plus 2 stays put. I'm just switching the x and the y. Well, okay, so I'm looking for the inverse function for this. Functions are always solved for y, so let's just do some rearranging here, shall we? If I wanted to get y by itself, so that this looks like a function again, I would need to subtract 2. So I would have x minus 2 is equal to 2/3 y. And I almost have the y by itself. I would need to, can you do that? I don't know, can you? Dividing by 2/3 is the same as multiplying by 3/2. So if we multiply both sides by 3/2, we get 3/2 times x minus 2 on the left. And on the right, when we multiply by 3/2, it cancels with the 2/3, and there is the y by itself. I do want to do a little bit of simplifying here, a little bit of cleanup. Let's distribute. 3/2 times x is 3/2 x, and 3/2 times -2 times 2 divided by 2, that's just a minus 3. Ladies and gentlemen, that is my new function. That function is the inverse of this one right here. For those of you out there that had tried to eyeball it, you would have been wrong because, yes, okay, this is 2/3, this is 3/2. But if you're like, well, plus 2, the inverse is minus 2. No, it's actually minus 3 for the way these come together. Again, I need these functions to completely undo each other. Now, please observe, I'm about to write a different notation for this. Instead of y, I kind of want to call it f of x. However, I don't want it to be mistaken for the original function, but I do want to say that they're related. So here's what I'm going to do is I'm going to put a tiny little -1 right here next to the f. This is f inverse of x, f inverse of x. This is the notation that says that these two are related and specifically are inverses of each other. So this function here is the inverse of this function here. I will say that again, please note how I read it so that you can sound intelligent. F inverse of x, f inverse of x. That is not, repeat, that is not a negative exponent. It's not. This is the notation for inverse. I'm sorry they look so similar. I can't help that. All right, last thing for pulling it together. Let's see what that would look like then if we decided to graph it, because what should we see? All right, so let's take this guy and let's see if we can graph this here. Here's my original. And blue, yay, right there. This is my blue line. And let's do the other one in purple again so we can kind of tell them apart from each other. So this guy's going to be in purple right here. -3 is my y-intercept. 1, 2, 3. Here we go. And my slope for that is 3/2. So up 3, 1, 2, 3 over 2, up 3 over 2, and so on and so forth. So this line, interestingly enough, goes right here. Okay. Do I still get this same line of symmetry that I saw before? Because I'm saying that these two functions are inverses of each other. Do I see that here visually? Yeah, actually, I still do. Can the graphs cross each other? Sure, but where do they cross each other? On that delightful line that we have, where y equals x, our line of symmetry, right there. Again, that is the line of symmetry. If you were to fold that between this side and this side, everything would match up perfectly. So again, we've got the visual for our inverse functions. Ladies and gentlemen, please, if you take away one thing with you today, this is it right here. The foundation of all things inverse is that x and y switch places. I need you to know that, because if you know that, you can build anything else that you need when it comes to inverses. Okay? Promise me not to forget. Thanks so much. Have fun. Bye.